Good evening, good morning, good afternoon, wherever you are in the world and when you're watching this. So this Facebook Live is about dealing with ROs, DIs, and fluid dynamics. In particular, we're going to be talking about the ID of hoses, how they change, from one hose to another hose to a tube, and then the managing of that. So this is not well scripted, I know what I'm talking about. So I'm going to try and start at the beginning, and then you can ask questions about fluid dynamics and getting water with a lot of pressure. Because what's happened is that if you go back to 2012, we developed the first water-fed brush with 4 jets, right? Before then, everything had 2 jets. And we had interchangeable jets where you could change them from being 1/24th of an inch up to 1/12th of an inch, or even 1/36th of an inch or something like that. So we understood flow, changing the flow makes a difference when you're on the glass. Then, over the last few years, then we've come out with hydroblade, and rinse bars are becoming part of, the way all water-fed poles and water-fed brushes are made, or there are bolt-ons to sort of compensate for that. This is made with a rinse bar. And so all of a sudden, you could have, in this brush, there's 13 jets, 13s, that's 39 plus 8, there's 47 jets. Some of you would have seen the post I put up yesterday where we've got a solar panel cleaning prototype brush using this, rubberized material. I don't know if you've noticed toothbrushes. If you buy expensive toothbrushes, you might find that they're more rubber than they are nylon these days, right? So there's a logic that sits behind that. And so we're sort of exploring that and sending this solar panel cleaning brush out to a good friend of mine to be tested. So, but this brush here, the one here, would have like close to 70 jets open. Mario is here. Okay. So what I want to do is go through from the beginning to the end as best as I can to give you all the information that you need to be able to make a well-educated decision about how water flows and how you get the right amount of water to a brush. So let's start with a brush. I don't think I've got handy, I could have done that, but a pencil jet brush. But you all know what a pencil jet brush has been around for 50 years, right? So a pencil jet brush has 2 jets or 4 jets like this, and you have pressure, and then that pressure, the cross section of the pressure, flow is a constant, pressure and resistance are interchangeable, right? So that's the first thing you've got to remember. Flow is a constant. At any cross section in your fluid dynamic system, pressure and resistance are interchangeable. Okay, so if I give you an example, you've got a garden hose. Let's say it's got a twisty thing that narrows the corner. So the flow from the garden hose in your yard is going to be exactly the same. And then you open it all the way up and the water just dribbles out like this, right? Or you take it off altogether and the water really dribbles out of your garden hose. Then you put the fitting on and then you start to tighten it up. What are you doing? You're increasing the resistance across the last point, So on this side is 1 atmosphere of pressure, right? Which is the pressure in which we live at sea level, right? Hey, George, good to see you, buddy. Doug Ruck is here. So, George, you might pick up some stuff, but we'll be putting this up on YouTube, so if you can't catch it all, right? So as you tighten this up, right, the orifice becomes less, that's the resistance becomes greater. The pressure is not the pressure, the squirt is not pressure, the pressure behind the resistance increases. Therefore, in order to get the water through the smaller orifice, it increases its velocity. So what we're talking about when we're talking about a water-fed brush and getting it to squirt is actually the velocity of the water through the jets, through the final orifices, the final resistance. The velocity is what determines how far, the distance that water will squirt. Okay, so if we increase the resistance, we increase the back pressure, which is a better term to remember when you're talking about your water-fed pole system. So you increase the back pressure, then the velocity will go faster through that resistance and give you more squirt. So that's why with the evolution and the introduction, good morning, Dante, of multiple jets. Now you'll see some people go to low flow and they put 1 jet every inch or whatever like that. but you don't get a water squeegee. The object of having a rinse bar across the top is to get a water squeegee where all that water joins together. Last thing on the glass is the water. And then with Constructor brush and window weapon, you'll see that we have a blade of bristles. I'll just explain some of the logics, the foundation principles of why we're talking about fluid dynamics, right? You'll see this is a blade. Now, actually, anybody with a Constructor brush knows that water doesn't go through this blade. It's a blade. It's not like a brush, right? It's completely different. So if you see, a brush where they've basically stapled bristles, folded bristles into holes in a plastic block, the water goes through. And you can see some of the other manufacturers have released sort of rinse bars with self-cleaning, or they've got rinse bars in the middle. And then what they do to make that kind of work so that they could leave that brush on the glass is they make the bristles more sparse. You make the bristles more sparse and you have to do more agitation strokes, which takes more time, which is counterproductive for a window cleaner. Like the object of Reach It is faster, better, safer. The intention of designing your new tools is that you can get on and off the glass faster, right? Not that you can meet a paradigm or a design principle that I can leave the brush on the glass. Leaving the brush on the glass is not the point. Working faster is the point. So when we have a bristle blade, it breaks the surface tension of the glass. All we need to do is get the water with enough velocity to sit here. And if it sits here, it inherits the broken surface tension of the glass, of hydrophobic glass, and then it inherits that broken surface tension, and hydrophobic glass behaves hydrophilic. Okay, so that's the logic, right? What's coming on behind it. Now, if we go back to the old days when we made, we had Wash It Pro. It's now called labeled Zero Pure, but you can see the RHG systems and the IPC Eagle systems. I mean, they're all designed back in the 2010, 11, 12, that sort of generation there, where we're all using 2 pencil jets and 4 pencil jets. So we're not really thinking about how much water, how much pressure, how much velocity we need until this evolutionary change in the design of window cleaning brushes, right? So now we have more responsibility to get more pressure at the base of the brush, so that, or more flow rate actually, it's actually flow rate. If we've got the flow rate, we can change the resistance and then change the back pressure and then change the velocity, right? But with a pencil jet, you're going to take the brush off the glass and you have a separate rinse phase, right? So you agitate, then you take it off the glass and you rinse. Now then you want the water to squirt 3 feet or more, right? So that you can control it and guide it, and you're backwards and forwards, and that's my history when I was a water-fed window cleaner. Okay, but with Constructor brush, window weapon, we only need the water to go this far, right? So we only need the water to get to here on the brush when it's on the glass, and then it just sits on top of that. Last thing on the glass is pure water. If the last thing on the glass is pure water, the window will dry spot free. That's the basic physics. Okay, so if you're going to start in 2019, hey Matthew, good to see you. If in 2019 you're going to invest in brushes that have got rinse bars, hydro blade, Constructor brush, I mean this is an integral brush, right? Designed to be like this, so it's not bolt-ons. Then if you're going to invest in this kind of brush, then what I find is that there's a lot of people that go, oh, I bought the brush and it didn't work. And then you find out why didn't it work. Oh, I couldn't get the water to squirt far enough. So it's the brush's fault. Okay, so that's what today we're going to address. It's not the brush's fault. It's nobody's fault. It's just physics, right? Flow is a constant. Pressure and resistance are interchangeable, so we can adjust resistance to get more pressure, to get more velocity. Now, that's just talking at the brush. So today's talk is actually going to go all the way back to the RO, to the spigot, right? To the booster pump, to the delivery pump. And I'll try and cover all of those points, right? Is that whilst our target is nothing else than how much flow rate can I get to the brush, and there's no advantage in getting more than what you need. There's a balance, and then after that, if you connected garden hose to this brush, it won't be any more effective than just getting the right tube to the right brush, right? For the internal diameter of this tube and hose here. Okay, so this is a geek out session. If you're not into geeking out, if you're not into education, if you think everybody should be dumbified and keep it simple and just give somebody something and let them work on it, that's all cool. But I think 2 years from now, you'll be coming back to watch videos like this. Yeah, because you'll want it. You'll want the education, because the education always increases income when you get to use it. That's why people get educated, right? So they can earn more. So, okay, great. Let's look at this. So, firstly, we'll talk about the pressure at the spigot. So you can have pressure at the spigot at 35 psi. Spigot is tap in our language, right? From Aussies watching this. So you can get 35 psi, 30 psi at the tap at the spigot, and you can get up to 100, 120. Right, so there's really crazy variations in what happens. Well, let's talk about that. Let's talk about why would there be different pressures at my spigot? Why is that not a constant? Why can't the water department just give everybody the same so that it works for everybody? Right, you hear that line? Well, the answer is this: that there's a water supply, right? And the water supply is either going to have a gravity feed, which you'll see in Iowa, Texas, places like that, where they have the big water tanks. Sometimes you'll see, if you go to India and places like that, they put water tanks on top of buildings, and that creates the gravity feed pressure. But in normal town supply, in a sophisticated town or city, then there's actually great big booster pumps, right? And then the booster pumps pump water through pipes, maybe 18 inches or bigger, right, as it comes out of a dam or out of an aquifer. So depending on that, where the water's coming from would determine the TDS of the water, like how many solids are in the water, whether it's been going through lime underground or whether it's just rain that's sort of run into a lake and the silt is settled, right, or a dam. Now, once they start pumping it, if they pumped it through Rhino tube, right, can you imagine how nice that would be for town supply to be able to supply every house in your city if all they had to do was run Rhino tube from the dam to your place, right? So that's not going to work. You can feel that, right? So they're going to have a great big pipe. Now, then it goes from the dam to the city, right, or to the town, and now it's got to spread out. So that great big pipe will be split, and it might be split into 2 or 3 or 4. But when it splits, the area of the pipe, if it was 10 by 10, it would be 100. Right? And you'd think, oh, I should get 5 by 5, but 5 by 5 is 25. So we can at 100 can make 4 5 by 5s without any loss, right? So now they can split it. Now there'll be, say, 4 5 by 5s, and then 2 by 2s are 4. You can get 6 4s into 25, right? So you could have 6 2 by 2s going off, and then there's 1 by 1. So 2 by 2 is 4, so you can get 1 by 1, right? What I'm talking about is kind of like making a square of the area of the internal, the internal area here, because that determines how much water is going to be able to get through that with less wall friction, right? Now, I don't know if you know, but a river, those of you who are fishermen, river fishermen, you'll know that the water flows slower along the bank than it does in the center. And the question is why? Well, the water is actually got friction on the bank. Now, water is laminar. Water can behave in layers, right? So when that water's up against the bank, the friction on the water against the bank will pass on some of that and create some turbulence on this one, less. So the water in the middle of an even bottomed river or channel, the water in the middle will flow faster than the water on the sides, okay? And so it is with hoses and tubes, right? That if you have a Rhino tube, the wall friction is going to have a greater effect on water in a Rhino tube than it would in Rhino high flow, right? You have a look at that. Can you see that? Yep. Okay, and then I'm going to show you Rhino flat hose. You can't see it now, but when this has got 30 psi of pressure, it ends up with a much greater. It's got basically double the area inside as Rhino high flow. Okay, so you're going to use the same principle, and you're going to bring water from your RO system or from your spigot to your RO or to your DI tank, and you're going to bring this water through larger to smaller, right? And what that does is that compensates for the pressure loss through wall friction. So it allows the pressure, you're rebuilding the pressure each time you reduce that. So when you get the water out of your tap at the house, right, then, what else do you call it? Anyway, you know what I mean. So you open the tap to run a sink or a bath or a shower or something like that. Then when you open that up, it's coming through, a 1/2 inch copper pipe or a 1/2 inch PVC pipe, okay? So it's come from this great big pipe, which could be 3 feet, depending on the size of your city, it could be 18 inches, and then it's come all the way down and gets delivered to your house in a 1/2-inch pipe. Okay, and so it is when we design our pure water systems. We want to have that same understanding of being able to reduce the internal diameter to maintain the pressure, because our target is that we have a flow rate with the ability to adjust the back pressure in order to get the velocity through the jets to get past the bristle blade and onto the glass, so that the last thing on the glass is we're not pressure washing or soft washing the glass, right? We've done all the work with the bristles and the water that we've used before that, and we're just leaving pure water on the glass. Okay, so let's break it down and say, firstly, we'll look at DI tanks, right? So this is a DI tank. This is a 1/4 cube. We've got some really nice developments coming with this, with the atomic resin, to make it easier to load and unload this one. But let's have a look inside it, just in case you've never seen. So somebody goes, oh, is one DI tank better than another? And the answer is no, look at it. It's a piece of plastic. That's what a DI tank is. It's a piece of plastic. Sometimes you'll see it, they're called FRPs, fiberglass reinforced plastic. So you'll see the plastic is reinforced with fiberglass, but that's to take it up to 150, 200, 250, 300 PSI. Those ones are rated, way higher than what we need as window cleaners. So we're able to give you a plastic DI tank, right? And then inside that plastic DI tank is what's called a riser, yeah? And basically when the water comes in, it's coming in around the outsides, right? So it's randomizing, so you don't want to have the resin all the way to the top. You want to have it like an inch or two at the top, so the water can randomize, because you need the water to be randomly going through the DI resin to get it to purify, right? And then it comes down through the DI resin, which is in the tank, right? This is in the tank, comes down through the DI resin, and then at the bottom center is the riser, which won't let the DI resins get through, but the water can get through. The water comes back up through the riser and comes out here. All water that went in came out pure and spot free. So this is DI resin. DI resin is the real ultra pure water filter, yeah? So there's very little pressure. There'll be 5 PSI pressure loss maximum across a DI filter, okay? So you don't have to worry about pressure loss if you're using DI only. So that's why one of the sayings that we have is DI for high, RO for low, because the higher you go, the higher you go on a building, every 10 feet is another 5 PSI of back pressure this way, right? So if your RO system is going to be taking pressure out and you need more pressure, right, then you could switch to DI, yeah, because DI doesn't take pressure. Now, this is flow red, yeah? So it's a sediment carbon, basically designed to protect the RO, and then there's an RO, and then there's a DI at the front, right? Because the final filter to give you spot-free water usually is a DI filter, yeah? Hi, Alan, good to see you, buddy. Okay, so let's talk about the RO. Now, an RO, if you imagine it, has got 2 sides. It's got an inlet side and it's got an outlet side, and in the middle is a membrane with tiny, tiny, tiny little holes that water, pure water, H2O molecules, little Mickey Mouse molecules, right? Those molecules can get through. Now, when there's a mineral in the water, right, it's got an ionic charge. So let's say it's calcium, 2+, right? Then it doesn't just attract 2 water molecules, because the charge is actually quite strong. So what happens is that the water molecules cluster around the mineral molecule, and it's that cluster that can't get through the hole, right? So, pardon me, it just can't go through. Very little of them can get through, right? They can't get through the hole to go from the waste, or the main line, right? So the water's pressure up here, the water's going this way, but it's pressure that way. What can get through becomes pure. What doesn't get through can't. So you need pressure. No pressure, no pure. Okay, so how do we get more water through an RO membrane? Well, we can either increase the pressure on this side, which we call a booster pump, right? Now, usually 110, 220 volt, they need a lot of power to boost the pressure, right? Or we reduce the back pressure on this side to maximize it. Or we increase the temperature of the water, which changes the viscosity of the water and makes it, easier for it to get through. Those 3 things are the 3 things you can do. So usually we don't fiddle with the temperature, we just fiddle with the pressure on this side and reduce the back pressure on that side. So we talked earlier about pressure and back pressure. right, then you know one of the causes of back pressure is wall friction. So it's cumulative. The longer the hose, the longer the tube with the wall friction, the less pressure you get as you go along, right? And if you need to boost that pressure again, then you're going to switch from a larger tube to a smaller tube, yeah? So if an RO takes pressure out of your available pressure in order to filter the water, the benefit for you is that you get really, really cheap water. And that's the only reason why you'd get an RO. If you've got soft water, don't get an RO, because its only function is to make life cheaper. It doesn't make better water. The best water comes out of DI, and the last filter on an RO system is a DI. Yeah, that's the proof. Yeah. So these are really pre-filters. These are all pre-filters to save DI resin. Okay. All right. So the way to boost pressure before an RO system is to get a booster pump, and the way to reduce back pressure after an RO is either to get your hose management right, and that's not either, both, and you can actually say, okay, the water that comes out of the RO system, I'm going to put into a tank. So therefore, there's no back pressure. It just runs out of the tank, and then we can still have a booster, and then from the tank, we have a delivery pump, and the delivery pump has, 45, 60 PSI pressure switch rating, 1.5 to 2 gallons per minute flow rate, and that gives us the flow rate we need to manage the fluid dynamic systems of hoses and tubes to get to brush with jets. Okay? Geeking, right? Geeking. But this is really, really invaluable. If you get this, and if you can actually get any of your team members to get it, even just in a simplistic term, you go from big to medium to small. That's all you need to remember for the hoses, right? The longer a hose is, that's thin. So we used to have a lot of guys use Rhino tube, 300 feet of Rhino tube, but they have big pumps at the front, right? So a lot of them, also had pressure washers and things like that. Now you can't put 150 PSI through Rhino tube or flat hose or Rhino high flow. It's a 100 PSI rated system, because that's all you need in order to get constructor brush to work or pencil jets to work. Certainly pencil jets, okay? So step one, booster pump. If you're using RO, use DI if you can, because it's the best filter. Step two, booster pump to boost the pressure in front of the RO, maximizing the water through the RO. Step two, reduce the back pressure from the RO. Use a buffer tank. Go to tractorsupply.com, or if you're in Australia, sylvan.com.au, and get an ATV quad bike chemical spray tank. Right, we're going to bring those out soon as well, like our own version of that. And then that water that will then drop into the tank, and then the pressure for the fluid dynamics to the pole becomes the responsibility of the pump that's on that tank. Okay. Now, the next step is to talk about hoses and fittings. So if you look at those of you who've got Rhino flat hose is made round and flattened before it sets. Right. So it's a very flexible, non-kink plastic. But whilst I think constructor brushes, patent pending, this changed the industry, changed how people clean windows, everything like that. Hey Scott, good to see you, buddy. We're talking fluid dynamics now. We've talked about RO, we've talked about DI. So if you look at Rhino flat hose, it basically, it's got a lot of crazy life. Right, I have been snow. We've got so many new products coming out. We've got so many, and then I had a little holiday. Blah blah blah. Long time no see. So Rhino flat hose is basically a 12, in metric it's a 12 millimeter hose. High flow is a 10 millimeter hose. Rhino tube is an 8 millimeter hose. Right. So you'd see 12, 10, 8, and you'd think that they are that their performance is in relation to 12, 10, 8. No. Rhino flat hose carries twice as much water as Rhino high flow. Rhino high flow carries twice as much water as Rhino tube, right? So you can split Rhino flat hose into two high flows. You can split high flow, a short length, like obviously you've got pressure loss on the way through, but you can split a high flow into two Rhino tubes and have no, if they're all short sections, you'd have no pressure loss across these sections, okay? And the other thing that we found from Rhino flat hose is that it acts as an accumulator. So you see some guys who are in the pressure washing industry carry accumulators. An accumulator is, I've got one there, but anyway, accumulator is a steel tank with a rubber bladder inside and air pressure from your pumped up, and basically it accommodates pressure variations. And what we've found, because this is naturally closed and it opens, it'll become anywhere from 12 millimeters to 15 millimeters depending on the pressure going through it, and then it'll actually adjust, so you get a very constant flow from using Rhino flat hose. The problem with Rhino flat hose is where I want to get into fittings, and this is probably the exciting part of the whole thing. Up until now, I need to look around. Yes, here it is. We have connected flat hose with this connector here. And you may see something that looks like incongruent. So when you have a look at this fitting, you can see that even though we've got a 12 millimeter hose, which has got to go over a barb, so the hose has got to go over the barb goes inside the hose, and then the water has to go from here through there and then back to here, right? And so we get a pressure loss across this fitting. So it's not because it's only once, it's not cumulative, it's a smaller pressure loss than if we were running water through Rhino tube continually. However, what we wanted to do was work out how to eliminate that for Rhino flat hose, and now we can. So this is Rhino flat hose, and this is what's called a push fit. So it's got a collar, and you pull back that collar. These are probably, with Rhino flat hose, it's not so good to adjust it. You put it on once, but I will show it to you in a second. There's a little bag of goodies that come, which is the Rhino flat hose upgrade kit, right? And it also comes standard with Rhino flat hose if you haven't got Rhino flat hose. Okay, so let me show you this way. So it has a collar here, and that collar pulls back, right? Now, if you haven't seen this before, let me see if I can get light in there. Let me see if I can get this light here. All right, and you may be able to see the teeth move. Yeah, you can, look at that. See that? So when I click it down, those stainless steel tiger teeth get pushed back. And when I let it go, they grip the hose. And that's how a push fit works, right? Now, if you see anybody has broken a push fit, what they've done is they've tugged the hose without releasing the tiger teeth, bent and broken the tiger teeth, and then they'll say that the push fit doesn't work. But the push fit, if you want to use a push fit easily, push the hose in push the hose, pull the shoulder, and then pull the hose, and it'll come out easily. If it doesn't come out easily, then you haven't got the tiger teeth released from the tube. Okay, this is a standard Gardena fitting, so you can see the OD of that. Now, how do push fits work? A push fit works as compared to a barb, and you can see that the ID is exactly the same on both sides. So I'm trying to think about this one. This one is an adapter push fit, right? So it's bigger on one side than it is on the other. So the ID of this one is bigger than that one, but there's nothing going inside the tube to reduce the internal diameter of the tube. So if we wanted to connect high flow, let me find the right one for that. Oh, maybe this is the wrong kit for that, because this is all, I'll come back to that, okay? This one here that's 8.8, that's 10.10. Anyway, so I will show you what the kit is, right? Here we go. Sorry about that. There's always got to be a glitch somewhere in my ability to keep this smooth. So this is part of the Rhino the Rhino flat hose, this is the Rhino flat hose adapter. And what we can do, where's my hot water? Brought a glass of hot water. I put it somewhere, did I? No. So I'm going to go and look for my little glass of hot water. Hang on 2 secs. And we're going to be able to put this into here and then connect it to Well, I'm sure it will show up later, okay? All right, so let's do this. So I'm gonna lower this down here like this. There goes the glass. And it's basically, the other glass I've got, which I stirred and everything, has got detergent in it, but I can't see it for the life of me. So this is near boiling water, maybe not. And then we will grab the Rhino flat hose adapter. I'm still looking everywhere for my glass of hot water, right? And then open this up. Can you see that? Sorry. Push that in there. Push that down like that. All right, and we're nearly there. Great. And we're in. So now I can grab a fitting like this and push Rhino flat hose with zero pressure loss practically into I can push it into a straight, so we can just join them together. I can push it into a Y and put two high flows, right? And then from high flows we can also go we could go to a Y with two Rhino tubes, yeah? Or we just use it as a joiner and go straight, yeah? So we have, with the Rhino flat hose upgrade kit, we've reduced the pressure loss across this fitting here, yeah? And that's gonna return to you a better flow rate. And that's what we're doing all the way through the whole system, yeah? All the way through the whole system, you're gonna get better flow rate by just doing small adjustments like that. Now the same logic, if you look at our 20-inch brushes now, our 20-inch brushes actually have high flow going straight to the brush, because the amount of water that we need to get all of the jets of a 20-inch brush working is actually supported by high flow, and the amount of water that we can bring to the brush with Rhino tube is insufficient to drive all of those jets the way we want to drive them, as long as it's subject to pressure and flow rate being available, okay? Alrighty, so that is my logic. First, you start with big, you go to smaller and smaller, and I would suggest that the maximum length of Rhino tube is about 75 feet. The maximum length of Rhino high flow is probably 75 feet, but if you've got pressure, you can use it much more, but 75 feet if you've got reducing pressure. And you can use up to 150 feet or whatever of Rhino flat hose, no problems. And then after that, you'd want to be looking at possibly hard wall braided hoses. Okay, any questions about that? And what you're remember that the whole function as to why you're trying to manage this is you're trying to preserve your pressure and preserve the flow rate. So you've got the ability to run bigger brushes. Why do you want to run bigger brushes? Because you can cover more surface area with the same amount of time. Now, obviously, the bigger the surface area, the less pressure you have on the glass, per square inch of brush. So there's a time where you want to go back to a 12-inch brush to get more pressure. And in window weapon, we teach that with window weapon, because the window weapon is actually a pad with an abrasive surface. So you're really looking to choose between a 12-inch and a 16-inch, depending on how difficult it is, what you're trying to remove from the glass, right? So if you've got more difficult, you should use less surface area. And I'm going to stress that over and over again. You see guys just trying to emulate a window weapon with a 9x6 pad. If you multiply 9x6, like X by Y, right? 9 times 6 is 54. And if you look at window weapon, it's 12, because it's got a curve on it. So there's 12 square inches. So there's 48, 4.5 times more surface area on a 9x6 pad than there is on a window weapon. So when the guy goes to do a scrub and it's not going to work anywhere near the same, because he's got 4.5 times less of his own pressure. He'd have to press 4.5 times more against the glass to get the same effect as he would with the same material from window weapon, right? I mean, the science is not only the surface area of the material, but the pressure being applied so that you get pounds per square inch on the glass for aggressive agitation, so that you have less strokes, so that you can finish the job faster. Yeah, faster, better, safer. Okay, question time. Well, constructor. Yes. Yes. Oh, Scott, I've got a buddy of mine from Ningbo here. He's coming over maybe in a week or two, and he said, "Could I go out in the field with somebody?" You know, he's not from where you're from. I think you're in Houston, are you? Anyway, he's I don't think he's from your area, but he wants to get his son involved in the industry. So I said, oh, maybe Scott would be the guy, because you've got, you know, your teams, and he could tag along. He's the technical guy. He actually runs these machines that make 300 square meters, so that's like 3,000 square feet of concrete a day or something. Like, he's super. It's an American technology. They ship this machine to all over the world. There's 3 of them in China, and well, you know, they're in Mexico, and everywhere roads are being built out of concrete. This machine is, right. It's pretty fascinating. Christopher Jones is here. So Christopher, just a quick summary, and then I'm going to bail this. You know, what is the principles? What we're looking for. Oh, just one thing. I didn't show you these. Right. These little clips are included in the pack, and the reason is that when you use a push fit, right? Let me use this one. When you use a push fit, remember that if you were dragging this hose along this way and a little rock or something caught this, it can open the collar, right? And then the hose pulls out. Or if you're up on a building, the same if you clip on a gutter or anything. There's all sorts of a bit of pain in the ass, right? If that happens. Excuse my crass language. So what you have is these little circlips that go in here, right? See if you can see that, right? So that little circlip is now in there. You see that? And that locks the collar. Nobody can ever open this now until you take this clip out. So for Rhino flat hose, where you're going to be dragging it through, you know, across toys, through gardens, over rocks, over landscape, around corners and all of that, it's really important that you lock off your collars. Yeah, so there's 20 of them in the pack. Like, you don't need 20, and we give you, you know, flat hose to flat hose in the pack, flat hose to Rhino tube in the pack, flat hose to high flow in the pack, and two of each of those ones. And this one is you get Rhino flat hose to Rhino flat hose in the pack, so that you can just cut and join Rhino flat hose, and then of course you get your connector back to your quick connect Gardena. Okay, all in the pack, and you get 4. If you buy Rhino flat hose new, then you get Rhino flat hose has already got one in it, and the standard pack has 4 of the stainless steel inserts. Okay, and you get a little. This is how we've evolved. You get a little instruction sheet how to do it, right? So you can even delegate it. How's that? Okay, any questions? I'll just have a quick look. Okay, back. That's an inbound phone call. Trevor's here. Constructor brush, Bluetooth and Wi-Fi. Yeah, I hope you found this interesting. Just wanted to say hi. Pretty well versed on the products. But you are actually. You're really a great customer. Thank you, man. Yeah, we're nowhere near the end of this yet. Like, we're really evolving. It's a funny phenomenon, because people don't. They want you to know everything at the end. But if you look at the iPhone 3 and you look at the iPhone 10, yeah, good, Josh, you got that. Yeah. So if you look at the iPhone 3 and you look at the iPhone 10, I mean, Steve Jobs, he saw the iPad, he saw the iPhone. If you haven't seen Steve Jobs and the bicycle, Google it, YouTube it, and listen to him. He saw it. He saw it clearly in his mind, but he couldn't get the pieces together. They have to go together one by one, right? And so it is with innovation and development, and, you know, and just understanding. You know, that there are revelations that come as a result of a revelation, that you can't jump over revelations, right? And as we develop, you know, we've got so many changes coming. Like, we're non-stop thinking, faster, better, safer. And yes, Peter, I'm going to see you in Australia early next week. It's going to be exciting. Yeah, so non-stop, you know, innovation. If we're relentless on getting you to clean windows faster, better, safer. Tim Cruz is here, new friend. Good to see you, buddy. Yeah, if you get a chance, watch this. I'll publish it in HD. It's really informative for some of the conversations that we've been having privately, Tim. In fact, it may have been what inspired me to do this. It's either you or another guy called David. But I really want to have a video which explains everything about fluid dynamics. DI systems don't use pressure. RO systems use pressure. So if you want to increase the flow rate at the brush, just with the RO, you boost the pressure before it, or you reduce the pressure after it by dropping it into a tank, like a tank from tractorsupply.com with a booster pump, with a delivery pump, a 12-volt delivery pump. Then now you've got the delivery pump, you now want to go through hoses and tubes to get to the brush, such that you have enough back pressure so that these orifices of these jets can create a velocity of water that preferably squirts around 12 inches, but will work if it squirts around 8 inches, right? And that's Constructor brush. Tread poles are on their way, John Iron. Yep, I've got the design set, so the drawings have been done, and I think maybe we're just waiting on the artwork for the handles, but it'll be sweet. We're going to do a 4 foot, 8 foot, and 12 foot. Nice little set. And then with the gunslinger, sort of the fact that we've got a gunslinger on a belt, there'll be a reach it belt, and there'll be a reach it pouch, and then there'll be a pole holder, that'll hold our poles. So you'll be able to carry one, at least the short one, maybe not the long one. Okay, so good. Yeah, I'll have a look at Revelation 12:11. Thanks, buddy. That's good. All right. So if you are watching this on YouTube and you get this far, then make sure you make any comments, ask any questions. Find me. The best way to communicate with Perry Tate is facebook.com/perry.tate, Tait. I'm very, very efficient at that. I'm horrible at emails. I find them completely snail and horrible, like mail. Nobody uses mail anymore, and I can't use email very easily. But if you catch me on Messenger, and then we can swap videos, we can swap messages. I can make video answers. Like I can be much more in real time and get much better use out of my time. That way. Okay, but always here we're looking to improve the speed at which you clean, because that's what window cleaning is about. Yeah. Okay. Signing out.